All right, it looks like it's 10:15 West Coast, 1:15 East Coast, and sometime in the evening where Kai is at. So I'm pleased to start the next session, and we're pleased to have as our speaker Kai Jan from the Max Planck Institute in Munich, who will tell us about soft gluon factorization at 2 loops in full color. Kai, please begin.
Thank you, Lance. Thanks a lot to the organizers for the invitation. It's a great pleasure to join this special Amplitude meeting via Zoom. Today I will be talking about a paper last year on soft gluon emission factors, 2 loops in full color. This was in collaboration with Lance Dixon, Enrico Ehrman, and Huaxin Zhu. And sorry, my screen cannot move.
Do you want to try it in non-playing mode?
Yeah.
Or do you want to exit and try to re-enter and see if it works?
Okay, maybe I just work this way. Yeah.
It'll work, I think.
Okay, so one of the main focus of today's talk will be on the factorization property of scattering amplitude at high loop order. So the general physical picture is that when there are external particles, unresolved external particles, the scattering amplitude factorizes into lower point amplitude multiplied function, which has universal features. So we would like to study these functions. In particular, we're interested in the soft gluon emission factor, which describes the limit where one external gluon becomes soft. In that limit, the tree-level color ordered amplitude factorizes on 2 particle poles. Therefore, the soft factor at tree level is dipole-like. And summing over the gauge invariant dipole factors gives you the well-known Icono factor. So the dipole formula should hold in the planar limit to all orders. It is since the soft gluon is only allowed to couple to adjacent color order neighbors. So in both n equals 4 super Yang-Mills and QCD, the dipole emission factor is known up to 2 loop order for some time. However, beyond the planar limit, it is not clear what loop corrections does to the soft factorization formula. And it is expected that a 2 loop order when the soft gluon can couple to 3 external hard particles at the same time, new structures might emerge. One of the evidence that the dipole formula needs to be modified at 2 loop order is the well-known quadruple correlation in the 3 loop soft amongst dimension, which suggests the existence of an infrared IR pole, which is unlikely in a virtual scattering amplitude, which is unlikely to be cancelled by the phase-space singularity when you integrate over a dipole-like emissions factor. So our calculation provides this missing information. We obtain the first correction to the dipole formula at 2 loop order in full color. It takes the form of a tripole emission factor, which has color and kinematic dependence on 3 different hard momentum. So what else can we learn from this result? And in general, what can we learn from the soft factor at high loops with high multiplicity? So one hope is that we can understand better the universal analytic properties of a higher point amplitude, which might serve as a strong constraints for bootstrapping higher loop amplitude beyond the soft limit. And another direct application of the soft emission factor is that it can be treated as an integrand for phase-space integrals. One could integrate over it to get the resummation formula for physical event shapes at hadron colliders, and it serves as a building block to construct IR subtraction terms at n-cube LO. And in addition to that, it is also interesting to study the process dependence of the soft emission factors in particular, how the soft gluon distinguish between incoming or outgoing hard particles. This is related to the conceptual issue with collinear factorization violation with initial state collinear splitting, which is crucial to understand better the factorization of hadronic cross-section at the LHC. So I will tell you how we introduce the method that we did for the computation. So we compute the soft limit of the scattering amplitude by taking soft limit at integrand level. This is inspired by the effective theory picture, where the soft gluon is coupled to light-like Wilson lines. And the soft factor is given by the matrix element of Wilson lines. These Wilson lines represent classical sources traveling in a particular light-like direction. The advantage of this method is that the Wilson line matrix element preserves to the great extent the symmetry of the amplitude in the soft limit. In particular, it is manifestly invariant under the rescaling of the momentum of the classical sources. Therefore, the soft factor can depend on only one energy scale, which is the energy of the soft gluon. After factoring out this overall scale, it can only depend on the angles between the directions of external momentum. So it might be helpful to do a stereographic projection to map the two sphere onto a two-dimensional plane. Therefore, you can see that on this plane, there are multiple points representing the direction of the soft gluon Q and some other Wilson line directions. And you can draw the circle which connects three lines and do a conformal transformation. And to map this circle onto a straight line, in particular in this specific conformal boost, we'll map these 3 points to 0, 1, and infinity on the real axis. And the image of the angle of the soft gluon will be mapped onto a complex variable z and its conjugate. And this variable z is the standard variable which parameterizes the cross ratios. So by doing this simple analysis, simple exercise, we can figure out the number of independent kinematic variables for the generic process with one soft emissions coupling to n-1 external hard particles. And so there will be 2 times n-3 plus 1 independent kinematic variables. So this one counts the overall energy scale of the soft gluon, which you can pick at this at xij variable, which is manifestly invariant under the rescaling of the hard momentum. So this allows us to figure out the general structure of the soft factorization at higher loop order. And it can be written as a sum over dipole and tripole and quadruple terms. And so on, these terms correspond to the number of the external hard particles that soft gluon couples to through exchange of the virtual gluons. And so each of these terms has its own perturbative expansion. The dipole term starts at tree level, and it can only depend on one variables. Therefore, its structure is determined to all long loop orders. At one loop order, it has written as uniform. It has uniform transcendental weight. And starting at two loop, it starts to depend on the matter content of the theory. So starting at two loop and beyond, you will see a new structure, which is the tripole emission factor, where soft gluon is coupled to 3 Wilson lines through non-planar diagrams. So this tripole factor can depend on a pair of complex variables, Z and V bar, which are just described. At two loop order, it's the first order that it appears. Therefore, it has uniform transcendental weight, as in n equals 4 super Young mills. Of course, at higher loop order, more interesting things can happen. For example, you could have a first quantum correction in a abelian theory induced by a fermionic loop. And in a non-abelian theory, this kind of diagrams will give you color structure, which is quartic Casimir. And of course, as 3 loop and beyond, you might also have the quadruple emission factors, which depend on one more pair of kinematic variables. So our calculation of these two-loop tripole terms will serve as a starting point for which allows us to understand better about these functions and might help us to develop further to higher loop in the future. So now let me move on to some more technical aspects of the calculation. We did, as I said, we did the calculation using regularization scheme, which is DIMREG, and with light-like Wilson lines. So in such a scheme, lots of diagrams will vanish. The only non-vanishing ones are the maximally non-abelian diagrams. There are only two types of them, A and B, and they belong to a particular integral family, which is symmetric under exchange of I and J. So the sum of these diagrams in this family will define an ordered tripole contribution. And the final result, in the final result, you need to sum over the permutation of the three Wilson lines, IJK. So there were 8 last integrals in this family, which forms the system of differential equations. And these equations has logarithmic singularities in the limit where two of the cross ratios vanishes, and also at the point where the volume factor of the flow momentum vanishes. And the differential equation can be brought into canonical form if you switch to the complex variable z and z bar. So there are only 5 alphabet letters in the solutions to these equations. And the last letter, z minus z bar, will drop out in the final answer once we chop up the epsilon expansion at order epsilon to 0. In order to classify what type of functions the final answer belongs to, it is helpful to do the analysis in Euclidean region, where all the Mann-Standard variables are negative. Therefore, the xij are positive. And the master integrals in the Euclidean region are real analytic in the sense that it satisfies the reality condition. And if z and z bar are complex conjugate, there cannot be branch cut in a complex plan. The logarithm in the final answer are logs of only has these 2 types of logarithmic singularities, and they correspond to physical singularities in 3 collinear limit, where Q is proportional to Pi, Pj, or Pk. Correspondingly, the variable z goes to 0, 1, and infinity. As I just said, at order epsilon to the 0, there are 4 alphabets. These things tells us that the function space of the final answer is covered by the simple harmonic a simple valued harmonic polylogarithm, which is defined through differential equations given certain boundary conditions. So we arrive at the final expression for the ordered IJK tripole contribution. It is written we write it in as the form that it is a matrix in a color space acting on the lower point scattering amplitude. It has 2 terms which are manifestly symmetric and the exchange of I and J. And the coefficients F here is the logarithmic function of uniform transcendental weight. And it has a nice expression written in terms of simple valued harmonic polylogarithms up to weight 4. So since these functions are simple valued, we can plot them. So here I show the 3D plot in terms of the imaginary part and real part of the z variables for the fz at order epsilon to the 0. And you can see that it has logarithmic singularities as z and z bar equals 1, but it is suppressed as z and z bar goes to 0. So it is suppressing one particular collinear limit, but singular in the other ones. So the final step is to write down the final solution, final answer by summing over the permutation among these 3 external legs, IJK. So there will be 6 terms of them, but we observe that only there were only 4 independent color and kinematic structures. This motivates us to write down an alternative definition of the tripole terms in terms of a sum over unordered tuples. So within each tuple, the sum over the permutation over ijk is implicit, is done implicitly. It can be written as decomposed onto 4 components. Each of them has an independent color and kinematic structure. And these 4 coefficients define a function d1 and d2. And here are their relations to the original f functions. So for these d functions, they are finite. They are suppressed as the soft gluon is collinear to pi or pk, and it is divergent in the other collinear limit. So then you can probably see more clearly that in the on the Euclidean sheet, if you take any collinear limit, the tripole contributions will be suppressed. For example, when q is collinear to I, and only the first line matter where these di's are suppressed. So now, so far we are only talking about the properties in Euclidean sheet, but to understand better about these, let's give a definition of these d functions in terms of simple valued harmonic polylogarithms, and it's given in the following. And as a cross-check, we have checked at the symbol level on these symbols of these functions, the grids of the two-loop 5-point amplitude in the limit where one of the external legs becomes soft. So next, let's move on to the physical region, and which requires us to do the analytic continuation of these simple harmonic polylogarithms into 3 types of different regions. So the first is the region where all the momentum are outgoing, and the other is the one is incoming, the 3 are outgoing, and the last one is the 2 incoming, 1 outgoing. These 3 regions are physical scattering region, where the Mann standard variables requires carries a specific I epsilon Feynman prescription. So for the A0 and A2 region, we find that although there is a non-trivial phase for the individuals in the standard variables, the cross ratios does not acquire phase. Therefore, the analytic continuation is trivial. We only need to take care of this second region, called A1 region, where 2 legs are incoming and the other 2 legs are outgoing. So in this region, one of the cross ratios developed the phase of negative 2 pi i's, which brings it to the next Riemann sheet. Doing the analytic continuation into this A1 region requires taking the monogamy of the simple valued harmonic polylogarithms around the z equals 0. So the way to do it is to take in discontinuities of the d functions from a bottom-up approach. Basically, we can first figure out the derivatives of the logarithmic functions and then integrate back. So in this way, we can build the analytic continuation of the logarithmic functions from the lower weight to higher weight. So the result is that this analytically continued d functions has a discontinuity which can be written by in terms of classical polylogarithms. Here, I showed a particularly simple expression of certain combinations of the discontinuity of the d1 and d2 functions. I will use this expression to explain what we learned about analytical properties of the analytically continued d functions. So here we can see that it is only given by logarithmic terms, but it is very different from the d functions which before the analytic continuation, because now it can depend on the ratios of the holomorphic over the anti-holomorphic variables. So what this means is that And after analytic continuation, the D function becomes some new function called disk A1 of D1 and D2. The argument of these functions are still Z and Z bar, which are complex conjugate with each other. However, these new functions are no longer real analytic. And in particular, they develop branch cut on the real axis for Z is greater than 1. So you can see that this, for example, this logarithmic term will develop the ambiguity across the branch cut. However, it always shows in a particular combination, like here, such that the ambiguity always cancels on the branch cut. These functions will still be continuous on the complex plan. So this particular analytic property is not a coincidence because it shows that the physical amplitude must be a continuous function of kinematic variables. It might be helpful to come back to this picture where we map the kinematic points, which are angles between the external momentum to the complex ZZ bar plan. So given that the ZZ bar are complex conjugate to each other, there's one-to-one correspondence between the Z and Z bar variables and the point in the kinematic phase space in the A1 region. And therefore, all these points, since all these points on the phase space is kinematically accessible, and there should be there are no discontinuities of the physical amplitude. In particular, and in the vicinity of this boundary, which are a circle, the amplitude must be continuous and ambiguities must cancel. So let us summarize what we learned about the analytical properties of the analytically continued D functions. They are continuous and differentiable as long as Z and Z bar are complex conjugate away from the certain a few of singular points. And since they are single valued, we can again draw a plot, and you can see that it is continuous everywhere on the complex plan. And in particular, we may construct parity even functions on these two combinations, which are well-defined and non-vanishing limit on the hypersurface Z and Z bar. So let me emphasize that these properties are not properties for the individual Feynman diagrams. In particular, it's not a property for the F function that we originally defined for a single ordered tripole contributions, which defines its own integral family, but it is only a property of the physical amplitude. We expect that these properties will offer strong constraints for bootstrapping higher loop scattering amplitude, not only in the soft limit, but in more generic cases. And indeed, it was verified that in the multi-reg limit of 5-point scattering amplitude in supersymmetric series, they also observed similar analytical properties. Next, let me move on to a slightly different topic about the strict collinear factorization violation. So in this part, I will focus on the collinear limit of the soft emission factor. And to give you a little bit of background, we would like to understand the mechanism of the violation of a strict factorization for the initial state collinear splitting. So the statement of the collinear factorization is that in the collinear limit, where a pair of particles are aligned with each other, the amplitude will factorize into a lower point amplitude multiply a splitting function, which has no dependence on the non-collinear external dynamics. So this strict collinear factorization is the generalization of this statement to all loop orders. However, the statement is, although it's obvious at tree level, it does not hold automatically a loop order. It is true for time-lag splitting, where both of the outgoing collinear particles are, both of the collinear particles are outgoing or incoming. And this is a consequence of color coherence. And in the other region, if one of the this collinear particles is incoming, like for example, I+1 is incoming, but I is outgoing, the factorization will be violated. So in this limit, although you can formally define a splitting function, but this function will depend on the color and the kinematics of the non-collinear external legs. So, and the physical origin of the breakdown of the factorization is related to the Feynman prescription and therefore the causality of the theory. And perhaps it's the most easiest way to see this is to look at the universal cosmonauts dimension, so which has an imaginary part coming from the phase factors of the Mandelstam variables. So in a one loop scattering amplitude, for example, and you would have a 1/epsilon IR pole, but it is imaginary. And if you take the collinear limit, where I and I+1 are collinear, then the difference between the original amplitude and the amplitude without the collinear splitting will start to depend on the colors of Ti and Tk, if Tk is a non-collinear particle, which is also incoming. So therefore, the splitting amplitude will depend on the color of the non-collinear particles. So there is a lot of studies on these mechanisms. So the main conclusion is that although there are factorization violation IR poles at the amplitude level, that because it has absorptive nature and it exponentiates to a great part of it exponentiate at the squared amplitude level, therefore does not contribute to physical cross-section. And the remaining term that does not exponentiate will not contribute up until into the fourth LO at cross-section level. Although it's, of course, it's not easy to make a quantitative study of the cross-section, physical cross-section into the fourth LO. And therefore, it's not clear whether the factorization violating effect will play a role in hadron colliders. However, given these two loops of the factor that we computed, we can make a concrete statement about the finite part of the cross-section at NQLO, whether the factorization breaking term exists at that level. And so the idea is to take the collinear limit of the soft emission factors, and in that limit, the soft factor will agree with the soft limit of the splitting function. So, for example, at the tree level, once you take the external momentum Q collinear to the one of the Wilson line P1, then in the kinematic dependence on the non-collinear momentum will disappear, and you can perform the color sum of the non-collinear, the color of the non-collinear particles, and then it will give you the such a term which agrees with the soft limit of the splitting function. And in general, for the L-loop dipole emission, you can do a similar analysis, and you find that since the dipole emission depends on the kinematics only through the single variables, and it will only have an imaginary part that depends on the collinear on the non-collinear dynamics, where the real part does not distinguish direction of the external legs. So in that sense, you can see that the factorization breaking effect is anti-Hermitian for dipole emission factors to all loop order, and it will contribute to the cross-section level at a higher loop order. I mean, the physical effect will be postponed to a higher loop order. So the most interesting part comes from the tripole emission factors. In general, we need to consider the two physical regions where the soft gluon is collinear to the incoming particle 1, and there are other 2 external legs which can be either incoming or outgoing. So this region corresponds to the A2 region, which we defined earlier. Here, since the analytic continuation of the tripole term is trivial, and we have explained that the tripole emission will vanish in the collinear limit in Euclidean region. Therefore, in A2 region, it will also vanish. The only non-vanishing part comes from the A1 region once you take the collinear limit of the analytically continued soft emission factor. And then the collinear limit of the discontinuity of the D functions does not vanish. So combining all the information.
Can I interrupt for a second? You're almost at the end of the question period.
Okay, I
So
will.
if you could, wrap it up fairly soon. Thanks.
Okay, so so combining all the informations we have about the splitting amplitude, we can obtain the square of the splitting amplitude at order RFS to the cube, which will contribute to the cube IO cross section. So in such a splitting amplitude in the space-like limit, you can the factorization breaking effect is not vanishing. In particular, there are 2 types of color structures. The structure on the second line will vanish since the color structure on the second line is given by the anti-Hermitian operator. Therefore, it will vanish upon taking the color trace at order RFS to the cube cross-section level. The only non-vanishing part is given by the first line. And it is a finite terms, but it is non-vanishing. So why do we care about the finite terms at order RFS to the cube? Well, the reason is that the splitting amplitude will generate phase-space singularities. Once the factorization breaking term exists, it will generate a new type of phase-space singularities, which is collinear. However, it depends on the color of the non-collinear particles. Once you integrate over the splitting amplitude, it will blow up, and the physical divergence can be captured by its divergence captured by a splitting kernel, which depends on the colors of all the particles in the process. So this effect is relevant for N-cube LO protonic cross-section for multi-high PT jet produced in the final state, for example, dijet production at hadron colliders. And the uncancelled, non-factorized IR poles will endanger the conventional picture of PDF or hadronic factorization pictures.
Maybe you could skip to your conclusions, Kai, because we're running a little behind.
Sorry. Yeah, so these from this so from this analysis, we can see that the factorization breaking effect endangers the standard PDF factorization, which is important for the understanding of PDF evolution and hadron colliders and for the estimation of theoretical uncertainties. So let me briefly summarize. So we provide the first result for the 2-loop soft emission factor beyond leading color. The result reveals interesting analytical properties, which might be useful for bootstrapping higher order scattering amplitude. And for studying the IR subtractions for phase-space singularities. The future directions will be first to go beyond 2-loop order, and also to beyond the soft limit and fully understand the collinear phase-space singularities that does not obey strict factorizations. So this will be crucial for the estimation of theoretical uncertainties. And you'll be also interested to apply the result that we observed to precision eventship of hadron colliders as a shortcut to understanding the phase-space singularities. And there, the N to the cube LO precision level is within reach. Thank you very much. That concludes my talk.
Thank you very much, Kai.
Windows or
Everybody,
devices.
yeah. Right. So I'm running a little bit behind.
Al que me gustaría que me apoyara un poquito más, Gerson, pero no logramos.
Somehow
With from the audience. I see one from Simone. Would you like to ask your question, please?
Yeah, a quick comment and a question. So the quick comment is, as you know, there's a hard. You showed formulas with which had 1/epsilon poles, but there also exists you can also ask about the soft limit of the hard function, and that should be a nice finite quantity which would have would be similar to what you showed, but would have the 1/epsilon poles cancelled. My question is about you mentioned this EFT of Glauber gluons for the factorization violation. Has this theory been used quantitatively to predict the violation that you see?
A specific effective diagram, this double Glauber exchange, was computed, and for this type of diagrams, we obtain the same constant that we obtained in the soft factor.
Great, I see. So you can match your result with a diagram in this EFT.
Versions of these different stories.
Very good, thanks.
Okay, David, do you have a quick question?
Yes, I like very much your expression for D1 and D2. You said that discontinuities are classical polylogarithms, but at weight 3, everything is classical. Have you looked at your expression for D2 and see whether that also can be reduced just to Li4s, or whether it involves Li22s?
Since we have taken discontinuity, this disk of D1 and D2 are weight 3 functions. So, oh, okay, you're talking about the D1, D2 before the analytic continuation.
Yeah, they're also Li4s,
yeah.
I think.
Yes, they're.
Okay, I think it's time to thank Kai again, and then we'll move on to Andrew. Thanks a lot, Kai.